Good morning, everyone, and thank you very much for joining us today. I am Tam from the Department of Computer Science, and Dhaval is a master student from Computer Science, and he has been working with me and Professor Vijay Asari from School of Engineering. And today, Dhaval will present a thesis with the title Advanced UNet for 3D Lung Segmentation and Recurrence. So now, please welcome Dhaval.
Yeah. Hi all. Nice to meet you. Thank you for attending my thesis. I'm Dhaval Kadia. I'm doing my master's in computer science and doing the thesis with Dr. Tam Nguyen and Dr. Vijay Asari. My thesis is in deep learning and medical imaging, having the title of Advanced UNet for 3D lung segmentation and applications. We are applying the UNet based deep neural network for the medical imaging and its application of the 3D lung segmentation. The deep learning is a part of machine learning. It's learning the features from data, and it predicts the outcomes and finds the error with the actual expected or the results and feedback those errors and makes the connection the corrections in the values. And at the end, we have the model that can be tested on the testing data to make the predictions. The medical imaging is a kind of visualization or analysis of the human body to diagnose the diseases and monitor its condition. And and having enough data, the deep learning has an advantage of to make the diagnosis perfect, and even if in the various situations. The lung segmentation is a problem of segmenting the lungs from CT scan, and it is removing the unnecessary volumes of the CT scan and simplifies it. The significance of it is it can be helpful for the lesion segmentation or infection segmentation, and it can be further useful to find or classify or segment the cancerous nodules or different the lung diseases, and also the accurate analysis of lungs and its respiratory movements. We developed the R2U3D net. It is having different modules, and it is taking the input of 3D CT scans, having the data dimensions 256 cross 512 cross 512, which is very huge, and having the existing architecture, the hardware, it's very tough task to make the neural network enough for such such a large data. So first we apply the downsampling twice, and we apply the neural network on bottom of that. We use the recurrent residual unit. The recurrent the unit is helpful for extracting the spatial dependency, and the residual unit is helpful for keeping the data flow as it is. We use the different length of this module at different levels of UNet. Since we are having the limited hardware, we have to configure the UNet in a fashion that we can utilize more depth. So we use the less depth in the beginning of the network, and more depth or more length at the bottleneck layer. The dilation is a kind of procedure or a functionality that is allowing us to have more receptive field for the convolution layers, keeping the number of artificial neurons as it is. we use the squeeze and excitation residual module. It is extracting the global average from the channels of the convolution layer. Then it is applying the poorly connected layers, and then it gives us the priority or the importance of different channels, and it multiplies with the original input, and then we apply the residual connection. We use the DSC, it is called a dissimilarity coefficient, for the major part of the loss function. And on top of that, we apply the logarithmic function that is extracting the values before sigmoid function that we apply at the end. So we use those values and apply the exponential part. And in addition, we use the cross and entropy, and we combine these two losses and apply some weight to them, and then we calculate the final loss. We use here the soft DSC here, and it is having the squared part in the denominator. This is our result, and the first column shows the input, that is the intersection, that is the vertical intersection of 3D CT scan. The second column shows the ground truth, that is expected result, and the remaining column shows the output or the predictions from our models. And we can see that they are quite accurate. We achieve some good results here, and we compare it with the existing research that is using 700 number of CT scans for training, and we use less number of CT scans, that is 100, and we do not use the data augmentation, and we achieve better results. That is 0.992 a DSC, a soft DSC, that is 0.5% more than the existing results. We apply our model for 3D COVID-19 CT scans, and it works, but we can see that it is failing where there is the severe infection. And the reason behind that is that our model is not trained over such data that is having the infected lungs and infections. So it will obviously fail in such situations, but we have the solution for that. The lung segmentation is helpful for the further tasks like the lesion segmentation or the infection segmentation, because it is simplifying the inputs. But we have some challenges for segmenting the infected lungs or infections. Since the infection annotation is a time-taking task, particularly for 3D data, that is, we are going. I mean, the medical professionals annotates the data pixel-wise, and it is very time-taking for 3D data, and this is one of the reasons such data is less available. Having the available data, there are other problems, like the different scanners may have a low contrast, may have some noise, irregular shapes, and some kind of complex boundaries. And for infections, they may have the variations in intensities, irregularities. They may have the uncertain patterns. The lesions may have different textures and shapes. So the lesion segmentation is a crucial task if the lungs are highly infected. So we have to have enough data for that, and there is the problem of data scarcity, particularly for the infected lungs, because we have to have such data. And I observed that in the month of May, the publicly available data were less. There were only 20 number of 3D CT scans available. By the September, there were 50, and by the last month, there were around 200 annotated COVID-19 3D CT scans. And for the practical application or so that the given model will not fail, we have to have the data in the number of thousands. So we decided to solve this issue of data scarcity instead of using the existing data, and we have developed a Lesion synthesis algorithm that we apply on the CT scans, and we generate some patterns and we insert them into the normal lungs data. So we try to solve the same problem with the normal lungs data, not the infected lungs data. And it is helpful for to find the infections or the lung and abnormalities. And also this research is helpful to annotate the infection that can be further corrected by the medical professionals. Our framework is using the Lesion synthesis algorithm that we have developed. It is using the normal lung CT scan and the lung mask, and we generate the synthetic CT scan using that. Then we take those synthetic CT scans and the lung mask and train the lung segmentation model that can segment the infected lungs. And we multiply the lung mask and synthetic CT scan, and we get the synthetic segmented lungs. And using that and the lesion mask that is generated from our algorithm, we generate we train the lesion segmentation model. And for the testing, we take the 2D and 3D COVID-19 CT scans. We apply our lung segmentation model on that, and we get the segmented lungs. We multiply that with the actual data, and we get the segmented lungs, and we then apply the lesion segmentation model, and then we get the lesion segmentation that is having the areas where the infection is. We have developed another model called MSU-Net. It is a multi-scale UNet, and it is particularly developed for the lung CT scans, so that even if the lungs are out of the CT scan, its boundaries are outside, it can work in most of the cases. We propose several modules like downsampling and upsampling modules and additional changes on that. And we use the squeeze and excitation module for inside the decoder. And we have the 7 number of levels, and we use the data dimension of 5 into cross 5 and 2, considering that a 2D architecture. And until the last layer, it is decreasing its dimensions, and at the end, it is having 8 cross 8 dimensions. And we use some less number of filters, 9, 18, 36 accordingly. That is quite less, but it is giving a good result. It is less because our model is sophisticated, and we according to the hardware resources, we could have such number of filters. Since the data dimension rates are decreasing in the bottleneck layer, and we are using the dilation, we have to use the dilation accordingly to the data dimensions. So we use more number of filters in the beginning of the network, and the less dilation rate at the bottleneck layer. So accordingly, we make some changes in the recurrent residual module, keeping a dynamic functionality, that is a different length at different levels. We add the a multi-scale dilation. We use a different dilation rate. Let's say it is 1, 2, and 3, and we use more number of filters in the upper level. That is more having the more number of filters for high dimension, the high dilation rate, and less for the low dilation rate, and more number of filters for in the bottleneck layer, a more number of filters for the less dilation rate, and less for the high dilation rate. So this is the overview. We use the dilation rate 1, 2, and 3. 1 means there is no dilation. 2 and 3 means that there is. So where the data dimension are high, we are using more number of filters. This is the proportion. Considering the first level is having 9 number of total filters, so it will be divided into 1, 2, and 6. If it is 18, then it will be like a double, 2, 4, and 12. So we are changing the proportion of the number of filters having the different dilation rate. We also propose that our custom downsampling and upsampling modules. For the downsampling module, we used a different kernel size. Let's say it is 1, 2, and 3. We use 1, 3, and 5. And then we apply the convolution layer having the kernel size 3. Then we add them, and we concatenate all of the outputs, and then we apply the squeeze and excitation residual module, and then we apply another convolution layer, and then we have the output. Now in the upsampling module, instead of convolution, we apply the transpose convolution. That is we are increasing the dimensions in the decoder, and the remaining things are same, except we are adding an additional convolution layer at the end. And at the end of concatenation, the number of filters are 4 times than the actual number of filters we use in the convolution layer. At different levels of the UNet, we use different number of filters for the downsampling and upsampling. We use 6 for the first level and 42 for the last. We propose the Lesion Synthesis algorithm that is creating the artificial infection-like patterns that we add into the CT scans, and it is not safe, like similar to the normal infection, but it can mimic or the help if we don't have the data. So for this, we first extract the lung wall, and we decide where the lung wall is. Then we analyze the lungs and its intensity, so that we can assign the patterns value at each pixels. And we consider the analysis of the lungs like this. First we decide the bounding boxes outside the lungs, but nearby the lung wall, and we analyze its values, and we take the median of that, and we finally take the maximum of these medians, and we consider it as the maximum value that we can put it while the infection generation. Then we use the normal distribution based noise. It is a simple noise that we add into the entire lungs area. The next task is the generation of the patterns that we propose. It it is having some procedures, and the for that we first decide the bounding box inside the lungs that at multiple places, and we decide the random places inside that, and it is based on the Gaussian distribution. So there will be more number of points nearby the center of the bounding box and less at its edges. And then then from each of those points we start applying the some intensity values that we decided, and then we traverse in 3D or randomly, and we keep assigning those intensity values, and we also modify those intensity values with some rules that we have developed, and it will be assigning the values from each of those points until the certain amounts of infection is not generated inside the lungs. This is the generated values at different places, and it is based on the pixel wise values. It is a kind of noise, but we have applied some rules, and it is highly randomized. We apply the some morphological operations like dilation. First, we apply the dilation. So the first column is having the pixel-wise assignment of different values, and we apply the different dilation rates, and we have different patterns. So it is like some thick patterns than the actual ones, and we decide the dilation rate randomly from 2, 3, and 4. This is the outcome of our algorithm. Since we are deciding the bounding boxes to insert the infection into, so we have there is the bounding boxes and its infection inside. So this is the synthetic lesion or infection. This is the demo of that is generated. So the dilation-based approach was used for the lung segmentation because it is creating some solid patterns, and it is helpful for the lung segmentation. For the lesion segmentation, we are changing our approach and we are making the these patterns more diverse. And for that, we are using different morphological operations, having different kernel sizes and the random values. First, we apply the dilation, and we select the random integer from 2, 3, and 4 for all of these operations. Then we apply the erosion 2 times, then closing, and 2 times opening. And then we get the output. And this output is giving us a diverse patterns. So each of the random kernels, it is having random values from 0 and 1. Consider having the 2D data and the kernel size of 2 and 2 cross 2. So it may have a 1011 or 1100, any of these numbers. So according to that the morphological operations will be applied. And since there are multiple operations, it will create different patterns each time. So you can see that this may be more diverse patterns than the earlier one. This synthesis is less dense, and since we are applying the erosion and opening, it is removing some areas and it is making less bands, but it is helpful for the lesion segmentation. This is the outcome for this approach. And this is the animation. You can see this is some less dense generation. We apply this for the lung segmentation, and we compare it with the model that we train on the normal lungs. The first row, it is showing that from the first column, it is the scan, second is the ground truth, and the third is the prediction. In the first row, it is we are considering the algorithm to train our model, and the second row is showing the model. It is showing the lung segmentation from the model that we train on the normal lungs, and you can see that there is a less difference for when we apply our algorithm, and there is some errors in the lung segmentation when we don't. This is the lesion segmentation. We first segment the lungs, and we take the actual segmented lungs, and then we train it with the synthetic infection mask that we generated, and then we test this our model for a COVID-19 data, and this is the result. And you can see that the infection is segmented properly, but it has some errors, but it is good since we are not having data, but we are using our own synthetic algorithm. We are applying the 2D model of the lung segmentation and lesion segmentation on the COVID-19 CT scans. The first column is having the actual CT scan. Then we apply our lung segmentation model, and then we apply the lesion segmentation model. And the fourth column is the heat map. It is showing the what areas it is having the more infection. The red is high and the blue is less. There's zero infection. Here at the end, you can see there are more false positive, but we are keep trying to remove it, and the work is in progress as well. These are the results for one data set. It's having 19 number of COVID-19 3D CT scans. We compare our results with one publication. It's using the thresholding and the region growing algorithm, and it is getting the DSC for corona cases and the pneumonia cases, and there is the average value of 0.64, and we only apply the thresholding while the lung segmentation and the lesion segmentation, and we get the better results using our model and the synthesis algorithm. there is a box plot. It is showing the average of this results and the minimum and maximum values from the test cases. And we also achieve the authorities lung segmentation with a 0.97 DSC using the R2U3D net. So finally, we have worked on the 3D lung segmentation. We have developed 2 models, and we have developed the lesion synthesis algorithm, and we can perform a robust 2D and 3D lung segmentation. And we can apply for the current pandemic. We have applied, and we have achieved good results. And the important thing is that we do not require data to train our AI model. Without having data, it is important to perform the same task that we want to, and we have achieved the state-of-the-art results. We have many future works, and we want to further analyze our research to segment the infection with some sensitivities with a different kind of infections level or the severity. We want to apply we want to apply some additional mathematical operations for better the lesion synthesis. We apply some. We want to apply the data augmentation techniques, and we also want to apply the frequency domain because it is having a different point of view than this domain. We further want to apply our research for the classification of COVID CT scans into the CT scans into the COVID positive and negative. Since this research is able to localize or segment the lung abnormalities, we can apply it for COPD, the ARDS and pulmonary embolism, or other kind of lung diseases where there is abnormality. Since our algorithm can be modified, so that we want to apply it for the retinal vessel segmentation and also to the other domains. We have presented our poster in the standard symposium, and we have submitted one paper to the IEEE Access, and we are preparing another paper for the lesion synthesis algorithm and our new model, and we will be submitting it soon. Any questions?
I wonder, can you go back to the slides to show me the difference, I mean, the segmentation about the infected lung and the normal lung? I probably missed that part. What the difference of your result on the infected lung and the normal ones?
Yeah, so when we apply the lesion synthesis algorithm and then we train the model on that, then we achieve some good lung segmentation. Then we don't apply our algorithm. So the second row is having the lung segmentation using the model that is trained on the normal lungs data only, and the first row is using our algorithm, and then we train the model on that.
Okay. I mean, do you have the images of the results between the normal lungs, and the infected? Right now, in this slide, is this the difference?
The difference is shown in the fourth column.
So the first row is the normal one.
No, it is the infected lungs.
Okay.
Yeah, and it is the same. We are using the same for the both of the rows.
So this scan image is the normal lung?
No, this is the infected lungs.
Infected. Okay. How about the normal ones?
Yeah, it is working for the normal as well.
Okay.
The problem is to segment the lungs from the infected lungs.
Okay, I see. You only just focus on it because I thought you're supposed to make a distinguish between them, right? That is the goal of the classification.
Meaning?
I mean, the goal of your algorithm, you apply segmentation on different lungs, right? Different class, either normal one or the infected one. And,
yeah, yes.
And then you need to make a decision whether it's infected or not, right? That is the overall workflow. So right now you show me in this image, in this slide, it shows the infected lung, right? After you apply the segmentation. I mean, where is the one that for normal ones or you don't have?
Yeah, it is earlier. So these are the normal lengths.
Okay.
Yeah.
I see. Okay.
So I have a question.
Mm.
So what's the percentage? That is, what's the probability for you to have a successful diagnosis using your method?
That we haven't concluded because the next task is the classification. So once we segment the infection, we can use those data for the classification task.
Yes, and then actually this is your purpose, right? To perform like a very successful or very accurate diagnosis for the data.
Yeah. I mean, our purpose was the lung segmentation, the lung and the lung lesion segmentation.
Okay, but yeah, I'm not very. Probably I'm late. Sorry, I'm late. So that's why I didn't get really the point. So what I guess is that your purpose is to still to build a classifier, right? Classifier based on data.
No. Our model is for the segmentation.
Mm-hmm. Okay.
Yeah.
Okay, I see.
Yeah, that's why I also feel that. So right now you only focus on just the segments, right? The original CT image.
Yeah. This is what really confused me. So here you just go to like a midpoint to the goal. Actually, this is just a midpoint, and you don't know whether it is doable for your ultimate goal, right?
Yeah. Yes.
It's just one step, but it's still interesting. Yeah, still interesting. You still need to finish the next step and to see whether it works well or not. Yes, very good. Very good. Thank you.
Yeah.
So any other questions from the audience?
Hi, this is Russ Hardy here. I had a couple quick questions, if you don't mind. I'm just curious, is all this data from, you used the 100 cases that are on the Grand Challenges website, or where did you get the cases?
Yeah, it is the Luna 16 dataset. It's having 876 CT scans, and we use 100 for lung segmentation and 500 for the lesion segmentation.
So those are from the Luna 2016?
Yes.
And you also got, okay, and the new ones from the COVID data set?
Yeah, it's for testing.
I'm sorry. What platform did you code everything in?
It's Python and Keras, TensorFlow.
Did you use PyTorch?
No.
Okay. How long did it take to train and test?
It takes several days. but I've been doing it for more than 1 year. Yeah.
So so training takes several days. That's with 100 images.
Yeah. Yes.
And then testing takes how long?
It depends on the number of data. It takes 15 minutes, 10 to 15 minutes.
I mean, for a single case, if you run a single case through your network,
it takes
CT scan.
For the only one task, either a lung segmentation or
We'll say the lung segmentation.
It takes 5 seconds.
Okay, great. That's the scale I'm looking
Yeah.
at. And so one thing I mean, it's really great work that you did. Congratulations. The one thing I just wasn't 100% clear on is what aspects of the networks that you used were new and what aspects were just adapted from, because you presented those very interesting and complicated art structures. And I wonder if, just without going into tremendous depth, can you describe in a very high level what did you do that maybe was different, or I mean, because I think just synthetically creating your disease lungs, that alone I think is a worthy project, even if you used existing networks. But I think you modified the networks a little bit. Can you just, at a very high level, what's different about your networks?
Yes. So we apply the different rates of dilation at different levels, and we use different kernel sizes for the upsampling and downsampling.
So you kind of optimized some of the parameters in the network.
Yeah, and also the kind of the data that we extract from the earlier level. Yeah.
All right, thank you. Good job.
Yeah, thanks.
Sorry, I have one more question. So, have you tried the different kinds of neural networks here to get the different results, and to see their different performances?
Yeah, I tried a different UNet that is from simple until the one that I developed. So eventually, the results were getting better since I was improving that.
But what kind of neural networks you use here?
I used only UNet.
Okay, I see. Okay, good.
Different generations of UNet.
Yes.
Yeah.
Yes. Yeah.
Any additional questions? So you can, if there are no more questions, you can go to the main screen. You can close the sharing.
Sure, yeah.
So once again, if any questions to Dhaval, please ask now. If not, only the committee members can stay and others can leave the meeting. The committee members will discuss with Dhaval a few additional questions.